Well, hello everyone. I'm Mariano Vasquez from BSc. I remind you that in the sheet that you have signed to the right, you will see a column with a number code. This number code is for those that have asked for a Mare Nostrum account for the hands-on sessions. So take note of the code. In the next sessions, you are going to see a separate sheet of paper with the names and the code. So take note of it. And in order to enter to Mare Nostrum, then I think that you have received the instructions, but it is very likely. Well, I think that you didn't have received the password and username. So this is the passwords and username based on that codes. So each of you just take. Considering the program, yes, hands-on, it's very likely that, yes, I think that hands-on start tomorrow. But in any case, you can just play around with your accounts at home, not now. You can play around with your accounts later and see what you can do. But in any case, those teachers that have asked for a hands-on session, they have already entered in their accounts and checked that everything is in place. So this course, just a quick question. Which of you are coming through Biomed project? I mean, through means that you have that the course have been advertised in Biomed webpage. So who of you are coming through Biomed? One, okay, all right. So in the last, this course has been repeated in the last years, but in this year we're doing something that it is different. The course is typically for HPC and applications of HPC simulations to kind of, let's say, real world, so to engineering applications. And in this edition of the course, what we have done is we have oriented it to biomedical research. And it is done together with a European project that it is called Biomed. I will talk about this later about this project because it is a very interesting one, I think. So the full edition is now dedicated to let's say, real world, or in this industrial, let's say, applications are going to be mostly related to biomedical research. If you look at this is the program of the course that you have already written down, but I have put here some colors. My talk is going to be kind of just an introduction of the course and the project and things like that. And you see that those that are in yellow are the courses that are mostly devoted to computational stuff. Those that are in orange are mostly devoted to organ level or tissue. And those in blue are those devoted to molecular medicine. So it kind of cover the full range between organ level and molecular medicine. So our project, Biomed, indeed has the same structure. It's computational tools for biomedical research, for simulations in biomedical research. So it covers more or less the full range of the simulations, that of the simulation realm. That's why I think it is very interesting. And also you see that there are some courses are going to be low-level courses on programming and parallel and coupling algorithms, things like that. Other ones will be are going to be hands-on, for instance, from Carl from Microsoft, or this is purely on computational stuff, and also Alexander Heifetz and Andrea with the molecular medicine hands-on. So it's going to be indeed a bit kind of a good panorama of the kind of things that you can do. These courses are mostly devoted to to students of master, doctorate, but also to persons that are engineers, that are related to private sector or clinical or doctors. I mean, it's a wide audience. So if sometimes you don't understand very well some slides, then just take it easy, because in the next slides you are going to understand. In any case, something that it is very important is, well, of course, in the hands-on, this is going to be very interactive, but in the rest of the courses, just feel free to stop everyone and ask whatever you want at any time. I know that mornings are difficult, but well, you can just do it. So, as I said before, so far these PATSI courses, the goal was try to fill the gap between different things, like computer science and computational mechanics, computational mechanics and bioengineering, academia and industry, academia and clinical research. So the goal is just that you just not use the software as simple users, but you understand what is behind of this software, not just to use the software as a utility, a tool, something that you do for doing something, but you really understand the tool, some of the underpinnings of the tool. Because by properly understanding the tool, you're going to use it better, and you're going to understand the range of application of each of the tools. So the goal of this course is try to fill this gap, try to help people to understand what's behind the tool in order to use it better from different realms, different background. I don't know if you have seen this TV show. It's a good one. And from this TV show, in some of my talks, I use a quotation from this TV show that is very interesting. Is that, well, to me, one of the characters says this to another character, that computers are not the thing. Computers are the thing that gets you to the thing. Which means that computers are very nice. They are very important, but they are kind of, in our field, they are kind of the cars that drives you to some place, some beautiful place. But they are very important, and the designers of these cars are very nice people. But you have to think that computers are what are getting you to the real thing, to the thing. So in our case, the thing is going to be the application of this course, which is biomedical research. But as I said before, the important thing is try to understand how the cars are made, so you can use them better. Well, for those of you that are not from Barcelona, I don't know if you know, well, these churches. These are the typical churches that you can see in Barcelona, like Sagrada Familia, La Catedral, and all these churches. So all these churches are relatively famous, except for this one. But this church is getting more famous because in this church is where we have Mare Nostrum, which is the computer that you are going to have access. So it is indeed very beautiful. It's inside this chapel. It's a very large computer. It's about 13 petaflops, which makes right now is the 4th or 5th supercomputer in Europe. And it is between one of the top 20 supercomputers in Europe. It is the 4th edition now. After this 4th edition, what is interesting of Mare Nostrum is not the size, which is very large, which is very nice for us. It is 165 cores. But what is interesting, it's a 4-in-1 supercomputer. So you have a very large partition, which is about 11 petaflops, and in this very large partition is kind of general purpose machine. It is made of processors very close to the processors that you have in your own computers. But there are also other 3 computers that are of different, is what we call emergent architectures, which means that they are different kind of computers. Like one is done with Intel K&H processors, which are the mics, they used to call mics. Another one which is made by Fujitsu with ARM. Another one made by IBM with NVIDIA GPUs. So the good point is that through Mare Nostrum you have access to these different architectures too. It's very nice because for us that we develop code, it's very good to have these different architectures so we can port our software to these architectures which are going to be very likely, one of them is going to be very likely the next generation of supercomputers. And also what is interesting is that you have access to them. Researchers around the world have access to this system. And I have to say, not because I am from BSc, but I have to say that support people in BSc are great. They are very, very good. So the good point is that the same operations department that are doing support in Mare Nostrum, in the large computer, they are also doing support in the other emergent supercomputers. So it's to us it's very interesting to have this computer here. So just a brief account of what is BSc. BSc is the course organizer. Some of the teachers that you're going to have in the course are from BSc. Other teachers are from the different partners of this Biomed project. BSc is the Centro Nacional de Supercomputación. It's the Spanish National Research Center on Supercomputing. It was established more than 10 years ago. We are right now 500 researchers, so it is relatively large. What we do is we do not just give access to the computer. We do more than that. We give access to the computer, but we are also researchers working to develop things that can use supercomputers. So it is not just technical, but it is also research. So the center is divided in departments. So as I said before, we are almost 500 researchers. So these researchers are divided in departments. My department is the Computer Applications in Science and Engineering department. Although we are going to talk about life science, there is another department which is the Life Science department. So in this course we are going to deal with things that are studied in the Life Science department and in the Applications department. So Life Science is mostly devoted to molecular stuff, genomics, and also bioinformatics, let's say, and computational biochemistry. But in our department we do different things. What we do in our department, the keywords of the activities that we perform is computational physics or computational engineering. So what we do is we develop software from the bottom to the top. Bottom meaning the very numerical algorithms up to parallel programming of the codes and usage of the code. So we are more than 90 researchers, so it is a bit 1/5 of the center is our department. People of different backgrounds like computer science, physicists, mathematicians, engineers, and also graphical designers. Then that's why you are going to see very nice visualizations here, because they are done by our graphical designers, which is not that common, but we have them. So if you look at the research lines, they are very techie jargon about what a computational mechanics group would do, like including big data, numerical, physical and numerical modeling, things like that. But the point is that our center is devoted to, it's by mandate, we have to work in collaboration with. So we work in collaboration with different scientific realms, with private sector and academia, with clinical research and academia, and we have application lines. So we have several application lines. You are going to see that myself, for instance, I supervise with a friend of mine. I co-supervise the development of one code that is called Alia. You have to sign there. Yes, and also just remember the code that it is written to the right. Yep. So I'm responsible for developing one code that is called Alia, and you will see that this code is applied in all these application lines. But specifically, we work a lot in biomechanics, and this is those that are going to the teachers that are related to Alia are going here in this course are going to be mostly in biomechanics. So this is our project Alia. Alia is a code that it was born about 12 years ago. Right now they are kind of in BSc. There are more than 40 researchers and that are developers and users of the code inside BSc. But outside BSc, they are kind of another 40. So it is a bit less than 100 people using and developing in the code. The code is the idea is to kind of recreate nature in a supercomputer. So this is sort of the main idea. So we develop a code that can be used in supercomputers to solve very complex problems. For instance, this is a wind field. Again, as we have very nice graphical designers, you can see that the visualization is very nice, but this is not just a cartoon. It's done with cartoon techniques, but it is science. So here what we are doing is simulating the I will turn off some of the lights. This is a project that we have with Iberdrola, which is the electricity company here in Spain. So Iberdrola gave us the topography of a wind field, and what we do is we just get this topography, create the mesh, impose some specific boundary conditions, and run simulations on it in order to see how is this wind field, how much energy is this wind field capable to produce. And also in Iberdrola they use the code for designing the wind field. That is to say, once they have the concession for the wind field, then they use this to design where to put the windmills. Of course, this is not designing a wind field is not something that it is done every day. So it's mostly used to study which is the power production that the wind field can have. So in this case, they are using the code. The fact is that, as I said before, we would like to recreate nature in a computer, but the more complex the system, the larger the computer is required. But the larger the computer is required, the more efficient the code is needed. So through this course, you are going to see what are the main issues when you have to program a code that must run in one of these computers. Because as you very likely know, this kind of, you cannot program, if you want to use efficiently these kind of monsters, you cannot program in the same way that you do for using a computer like this one. So the good point is that in our case, and in most of the cases, some of the cases that you are going to see in this course, the code was born parallel code. The development of the code is as a parallel code. It wasn't a sequential code that was parallelized afterwards, but it was a code that was born parallel. So this gives a different perspective on how to use this kind of computers. And right now, today, you have very good tools for doing these kind of things. So several years ago it was kind of difficult, but right now it's not that difficult, and you can do it by yourself if you want. Otherwise, you have very good tools for doing it. So this is what we call high performance computing, but also what is interesting is that something that it is relatively on the hype and new, this high performance data analytics. Data analytics is something that it is right now kind of fashion. And it is how to use these large computational resources to explore data, and this is something that we also do, and I think that you will see some throughout these courses. This is another example, just to give you some examples of something that it is not bio. This is solved also using our code. this is combustion. This is a problem that it is. These are the combustion chamber of a gas turbine. Gas turbine can be an aircraft engine, but also can be an engine for producing energy, electrical energy. So combustion processes are very, very complex, and this is something that you are going to see all along this course, which is, in fact, I think that there is one of the courses devoted to that, which is multi-scale coupling, multi-scale and multi-physics coupling. So right now, what you try to do, is to solve one problem efficiently in a large supercomputer. It's doable right now. You can do these kind of things very efficiently. But what is more difficult is to solve couple problems. When you have to couple fluid mechanics with combustion, fluid mechanics with aeroelasticity, solid mechanics with thermal flow. This is, if you want to do this in an efficient way, is more difficult. So this is the typical example of a difficult coupled problem. So what we teachers in this course are typically, these are the kind of keywords of what they do, is you always have complex geometry, complex and conventional physics and mathematical models. Pre-processes can be very complex in order to generate the data for running the simulations. Post-process is very complex too, because you're going to have very, very large data files and difficult to be analyzed all together. Problems are going to be multi-physics, large-case simulations. Finally, you're going to have difficult visualization and big data management. One of the courses is going to be given by Guille, that works with us in visualization. So one of the graphical designers that work with us is going to give you a course, and I really advise you to be there with eyes wide open, because he's very good doing these kind of things. So finally, what we have to do is this efficient and accurate software for supercomputers. How we handle that? Supercomputers are, as I said before, very large monsters, and they are kind of Shrek, because they are good monsters, not bad ones. But as Shrek, they can have difficult character. So you have plenty of components of different manufacturers with different pieces of software right now running in the different components. So which means that if you want to do something efficient for running in these kind of computers, you have to go part by part, analyzing each of the bottlenecks that the code can have. So in one of these courses given by Ricard, is going to be today, you are going to see again a graph like this one. So in this graph, what you can see is that these are kind of the, let's say, efficiency pyramid of programming. So you have to think about how you work in a single core, even if you are going to use thousands of cores, but you have to be skilled enough to, for instance, in this case, you have to teach the compiler what you want to do. In general, the compiler is something that you just write the code and you expect the compiler is doing everything. It's fine, more or less. Compiler is going to do something, a binary that you can use. But sometimes you have to program in a way to tell the compiler what you would like to be done. This is typically done at this level, and it's typically related to vectorizations, for instance, of the code. So the compiler is going to do it, but you have to help the compiler to do it. Then when you have right now the computers are multi-core. You see in telephones you have kind of 8 cores. In these computers right now, not in this one, but in more modern computers, you can have 32 cores, something like that. Which means that you have workers that are going to use the same memory space. So there are some specific tools that can improve the efficiency of a code in this specific scenario. And this is what we call the many threads efficiency. So you have to look, this is what we call the threads. So you have to program in a way that this many threads efficiency is achieved. Then you can focus in many cores efficiency, because right now a computer like Mare Nostrum had several nodes, what we call. So in nodes you have many cores, but then you have another node another neighboring node, and another one, and another one, and another one. And if you would like to use all these nodes, then there is a third level of parallelization, because right now it is not just workers that have access to the same data, but workers that will need access to data that it is in another place. So this part of programming and efficiency is very delicate, because in this case you need to write the code specifically for doing that. There is no compiler that will get what you write and efficiently divide data and work. No compiler is doing that. So at this level you have to write the code for doing that. You have to. This level is usually now is less forgotten, but it is usually forgotten, because in this case this is done also at the supercomputer level, which is where you have many nodes. But in this case it's like this is what we call each of these threads that are divided in different nodes is what we call the MPI tasks. So in this case what you are going to have some kind of a family of MPI tasks that are going to be to solve one problem, and another family of MPI tasks that are going to solve a different problem, but both of them are coupled. So it is very important how you make communications, because these two families. You can think that this is one family and these are more families, so you have to communicate to the different families. And finally, last but not least, is that if you are solving very large scale problems, it is very frequent that you are going to produce a lot of data. It can happen the other way around. For instance, if you solve fluid mechanics around an aircraft, for instance, this is a very large scale problem, and you solve plenty of degrees of freedom, and you may need one full supercomputer to solve the aircraft, to get only one number, one real, one long byte, only one number. Why? Because they want to reduce the drag, and the drag is just a force, it's just a scalar, it's one number. So you say, I'm going to use a very large supercomputer for hours in order to get only one number. Yes, but there are other cases where they don't want just this number, I want the pressure field in the wings, and I want the streamlines just moving around the aircraft, because I would like to study the effect of the vortices behind in the wake of the aircraft. So in this case you need a very efficient way of writing data on the fly once you are running the case, write data, and many times to read data. So this is another, and then thirdly, you need to explore this data. You need to, offline, you need to have access to this data and explore it. So it's indeed a very difficult issue in itself. Okay, this. Okay, so the good point of the things that we do here is that we are going to talk about biomechanics in those that are coming from BSc we'll talk about biomechanics. The good thing, at least to me, the good thing is that I'm not a biologist, neither a physiologist. Until very recently, I didn't know how many lungs we have. I know that we have one, so I'm just getting educated. So we are not biologists that developed something because we need it. It's the other way around. We are computational mechanics people that develop codes for other people to use it. This is give us a different perspective, and in the case of our code is one of the few codes, multiphysics simulation codes that are developed at a supercomputing center. which means that if we do not do things efficient enough to use these large supercomputers, we are fired. So the good point is that, well, this is not a good point for us, but the good point for the rest of the world is that in general what we do is, let's say, relatively efficient in a supercomputer, so you can ask us to program or to develop whatever you like. So what you are going to see from our teachers is something that we call Alia Red. Alia is the name of the code, and red is the word that we use for grouping all that is related to biomechanics where Alia is used. So what we do is the simulation tools for biomedical research. We mostly work at organ and tissue level. You're going to see the differences of working for organ. And mostly we're focusing cardiovascular and respiratory system. In this course, you're going to see from our side mostly cardiovascular applications. So just a few words about Biomed, which is this European Center of Excellence for Computational Biomedicine. I think it's a very interesting, and for those that are not coming through Biomed, I advise you to take a look at the web page. Because it could be very interesting also it's very good for training, but also for having access to tools. All the tools that you are going to be here can be accessed through the center. So it's a very nice idea. What we would like to do with this Center of Excellence is to try to advance the role of computationally based modeling and simulation in biomedicine. In fact, what we are doing right now, we are teaching courses for bioengineers that are related to the project, but what we are going to do, we are planning for the next edition of the project is to give these courses to medical students. So computers are pervasive, they are everywhere. Any of us have several computers on board. You have the telephone, the computer, you have the Fitbits, you have many computers even that you are wearing. What we would like to do is also to bring these computers to simulations for the biomedical realm. Typically this is for predictive, not just for not to analyze things that already happened, but also to predict and be used in diagnose or just to project some healing treatments. Typically these applications are comprised by multiple components, so we work also in how to automate some workflows of these in these components, and the cornerstone in high performance computing. These are the core partners. It's very nice. It is coordinated by UCL. You're going to have one of the teachers, I think tomorrow, is Andrea Townsend, tomorrow, don't remember. Andrea Townsend, that is coming from the coordinator, which is UCL, University College London. So the core partners are from academia, are supercomputing centers, pharmaceutical companies, hardware manufacturers, pharma services. So it is like services companies. So it is like a very nice bunch of partners. So what we would like to do is to identify these user communities and the needs and help them to use these tools. The first initial targets are cardiovascular and respiratory, musculoskeletal systems, and molecular medicine. You're going to have a sample of all of them in this PATSI course. And this is what we would like to do. What we would like to do is to keep on developing tools, but also deploy these tools in supercomputing centers so people can have access and use these tools. The usability of these tools are sometimes not that easy because they solve complex problems. For instance, in our case, our code has no graphical interface, so for some of you it can be a bit difficult to be used, but however, we are on it. Sometime in the future, it's going to be some kind of graphical interface to be used. So the idea is that we have two things that we call the fast track and the deep track. So in the fast track is something code that is already developed and we help people to use it. And the deep track is users ask us to develop something and we develop things in the code for other people to use. And it is kind of a layered architecture. So you have different layers. We work at different layers: how to create the data for the simulation, how to run the simulation, how to analyze this simulation, how to include eventually a data analytics layer, things like that. So each of these layers has this fast track and deep track. You will see this in some examples. What is really complex is that not all the codes have the same kind of licenses. You have some very restricted commercial license codes, which are typically not installed in supercomputing centers. And you have on the other end, you have very open source licensed code, which are sometimes very difficult to use, but at least it's there and it is open source. But you have also codes like, for instance, ours, which is open access, that the code is, it's very likely that you don't care about how the code is programmed, but you would like to use it. So in this case, the code is installed in supercomputing centers, and you can have access to the supercomputing center to use the code to simulate something. So this is kind of what Biomed is doing, is sort of code infrastructure that goes on top of supercomputing infrastructure. And to provide kind of, we are not providing the direct access through Biomed, but at least if you have access, you can ask access through PRAISE or your own university or the very supercomputing center. You can have access to both of the resources, I mean hardware and software too. What we are doing is we are deploying this infrastructure. The project started about 2 years ago, so we are just doing these kind of things. Okay, so all right. Also, as I said before, you can visit this Biomed. The website is combiomed.eu, and you can visit it. And also, this is kind of a hub where you can do all these kind of things in this hub, and also have doing these codes is not just the code is not there just for you to be used, but also we publish and we write papers and we give advice and technical reports for people that want to use these codes, other codes, or program their own codes. So an example of Biomed, a very nice example, is this course. Because in this course you are going to see all the layers, and you are going to see, in fact, you are going to see how to use this code. So that's why I think that this is the course is interesting in this respect. So I think that we can just make a short break now, 10 minutes, 15 minutes break, just before we start with this computational biomechanics. So just I'm going to make a brief introduction of the kind of things that we do, the biomechanics stuff, those that are related to organ level and are related to cardiac and respiratory. So first of all, this is kind of this is a definition of applied mechanics. This is mostly an heritage of American science, is that they call mechanics, this mechanics is something that, applied mechanics is something that it is related to, it is used everywhere, right? But it was kind of born there, this name of mechanics. So mechanics is, it's theoretical physics. Applied mechanics is theoretical physics, and it's the study of systems governed by forces. In general, then it is kind of extended to, because systems that are governed by forces are generally ruled by differential equations, so then you can use the differential equations for other kind of systems that are not just governed by forces, but in an extension, you can say that, well, this is the main definition of it. If you think about computational mechanics, it's a subdiscipline of applied mechanics where you use computers. But when you use computational methods are not just a computer, but it is the computer, but it is also everything that is related to the mathematics that you need to develop numerical schemes to solve these equations, everything that is related to physics, that is related to how you create these, how you translate physics to the mathematical language, and it is also related to programming tools and programming strategies for doing these sort of things. And then you can go further and you can move to biomechanics. So biomechanics is, and computational biomechanics. So these are some definitions that are taken to this very nice book. It's a seminal book. It's a very nice one, very well written. And they have some, well, just mechanics applied to biology, but what it is very nice is this middle name between biological structure and function. Because you'll see that biological systems are very special ones, and they are very much difficult to understand than other physical systems, because they are related to life. So one mystery is how this structure is related to function. Why this was created, let's say, by nature in this way, is deeply related to what is the reason for. So what is the function? So the interesting thing of this biomechanics is that through these methods you try to understand how this structure is related to function. There is another very nice paper which is this continuum biomechanics of soft biological tissue. This is a very nice paper, and also you see there some of these concepts that you have to think that the goal of biomechanics is the improvement of human condition. So there are, behind biological systems are humans, finally. Okay, you can study nature through it, but the fact is that we are living there, and it is, in biomechanics, the idea is just to try to do something to improve the human condition and try to understand disease and try to understand how to heal this disease. So the goal of these tools is that they must help you to understand these very difficult systems in order to understand the healthy situation, to understand the disease situation, trying to understand the differences, trying to understand why, and try to think about how to help people to be healthy. So to understand how to diagnose diseases and to understand how to treat these diseases. Along this course you are going to see, I hope, the utility of these methods and under this respect. The computer is not going to heal you, not at all, but we hope that it will help the doctors to heal you. And the important thing is that this final goal of biomechanics. Again, I advise you to take a look at this paper. It's very well written and very nice. Typically, these are the sort of, let's say, engineering stuff. So engineering stuff is relatively well ordered. It can be chaotic, all right, but you try to understand something that it can be very difficult, but well, if it is engineering, it is something that is designed by humans. So it is sort of, you can understand more or less what is behind. It's difficult to model, but somehow you can understand it. These materials are kind of metal, plastic, rubber, whatever. But biological systems are different, are more like this. Biological systems are kind of a group of individualities that are sort of acting in a way that the team, like a team, but they are sort of individualities. So it's much difficult to understand how they work and to model them. Typically they are multi-scale, so you have many different scales at play. They are multiphysics. By multiphysics we understand that fluid mechanics and solid mechanics, when they are coupled, we call that this is multiphysics, because fluid mechanics are following the same physics, right? But fluid mechanics are following some governing equation, and solid mechanics are different ones. So from the computational point of view, this is adding a difficulty. And they are coupled in very high complexity, which means that you can solve each problem individually, but when you couple them, maybe everything is spoiled, because the the solution can become unstable. You see that physically this is happening, but when you try to model in a computer, you get very different answers. Even if you can solve properly the individual systems, when you couple them, you're done. And the fourth and most important, most differential point is that these kind of things, the emergent macroscopic properties, which means that the very low scales can have decisive influence, will have decisive influence in the upper scales. So you cannot neglect them. In any way you need to model these lower scales. Even if you are not solving them, you need to model these lower scales because they can be very decisive upwards. It's like if I have to simulate water, I can simulate this water inside the bottle. We can have computational fluid mechanics and try to simulate it, and of course we are not simulate molecule by molecule. In biological system, in tissue, you are not going to solve to model. If you want to model a heart, a beating heart, you are not modeling each cell, but you must include the cell model. So why? Because these emergent macroscopic properties are decisively ruled by the lower scales. So even if you don't do this, you have to take this into account. So in the course you are going to see different individual scales. You are going to see from molecules up to organs. You can understand the difficulty when you see the orders of magnitude between each of the scales. So if you go from molecules to small vessels, you have kind of 7 orders of magnitude. If you go to a heart, you can add another order of magnitude. If you go to a human body, another one. So really there is a very large disparity between the scales, physically and time scales also. So it's the question is how if I cannot simulate the molecules in order to simulate a full heart, then how can I include all these scales in the model? You have to be very clever to do this, and that's why this biomechanics is very difficult to modulate. What is interesting is that if you look at this, well, I have this is a very nice picture which shows these scales and organization levels. What is interesting here is that just data acquisition techniques are different from at different levels. Data acquisition techniques are the things that are going to help you to create the simulation scenario and to validate or, let's say, verify what you are doing. So they're of completely different modalities. You have these in the heart. When you'll see heart or bone simulations here in this course, you will see that typically this is coming from CT or MRI or PET. Well, different things to try to understand to acquire data. However, if you go to molecular model, you are going to see something absolutely different. Everything is completely different. And what is difficult is it's a language problem. When you do molecular dynamics and when you do organ level, it's difficult among us to discuss one with each other. So at some point, each of these levels can be thought as a separate compartment, which is wrong because it is not separate compartment. At least you have to establish some kind of relationship between them. Backgrounds are different at each level. For instance, if you go to what is nice of these scales is that it even includes healthcare organization. And it is very relevant because right now it is very fashion to talk about big data. Big data is data that is coming from individual patients, a lot of data, like from their clinical histories. So how can we integrate this data that is coming from epidemiology, from analysis of statistical data of people, down to the molecule? So it's not that simple. And it is, you are going to have even communication problems between the levels. What is interesting also is that even the names of the disciplines are different. For instance, at this point, if you go down to the cell, you can think about biomechanics. But if you go from the cell down to the molecule, people talk about systems biology or molecular medicine. So we are not sharing not even the same conferences. In BSc, we are not even in the same department. We are not even in the same floor. I mean, we are at third floor and they are at second floor. So it is very difficult to communicate. Languages are different. However, you can see all of us in the same slide and in the same realm because we are all human beings and we are connected through it. So what is difficult is to try to establish the relationships between them. You can focus in one of them and it is fine, but then what is difficult is to be multidisciplinary and try to establish these different relationships. But, for instance, I work at organ level. I work in cardiovascular and respiratory. I cannot isolate myself. What you need, you cannot isolate the organ simulation and you cannot isolate my discipline. So you need, at some point, you need connections between the different levels. This is a message that I've given you in this introduction, but you will see this message all along the course. In fact, so here you are going to have teachers from computational realm, teachers from organ level, like bones and cardiovascular, and teachers from molecular level. Well, these different teachers are going to have dinner tonight, so we are going to try to make some connections between us. But it is, in any case, it is very difficult, very difficult. So let's talk about tissue, just for you to see at what extent is difficult to simulate and to create these simulations. The fact is that how these tissue cell properties can emerge to upper levels. Which are the mechanisms that makes these emergent properties come up? So the fact is that the response to tissue depends very deeply in the internal constitution. So one example are forces. If you make some forces on tissue, this depends very deeply in this internal constitution. It's good for me. I repeat again. By training I'm physicist, so I'm not physiologist. So it was kind of it was a progressive learning, and it is in some of these. Then you can ask me also for. There is another very nice book of Humphreys, which is very good for us, for people like me, like physicists or engineers that are just getting slowly to this stuff. So this is kind of my own introduction. What is this? And it has a view of a physicist or an engineer. So what you see is that the response to forces depends on these very decisively on these three issues: the cell biology, the histology, and the surrounding conditions. So cells are kind of the constitutive parts of tissue, and that's why this is difficult. So in this point you see this analogy of a team, because the cells are like the players of this team. So they can grow, move, function, communicate. So how are you going to simulate something that the constitutive parts are so independent? They can do all these kind of things. So just a few words about the cell biology, just to see that even the cell is difficult in itself, is that these important things are these the parts. So this is the first and most, to me, the most appealing stuff, is the genetic info, the genetic information. The genetic information is just in the nucleus of the cell, and every cell of us has the same genetic information. So it's the nucleus is like the safe where this genetic information is kept, and something that to me is kind of absolutely magic is the phenotype. Is that all the cells have the same information, which is all the information, but they know by the environment and some genetic coding, they know what kind of cell they must be. They can be whatever, but they know, especially upon environment, they know what they can be. So this is the magic of stem cells, that the bones, for instance, bones and muscle cells, they have the same information, but they know that they must become bone, and they know that they must become a muscle. So this is very interesting, and this is what makes the difficulties kind of to try to model these sort of things. Then you have the cytosol. This is important because it is mostly water. So cells are kind of bubbles of water surrounded by a membrane. So everything there is almost mostly water. Then you have this skeleton, this cytoskeleton, which makes the structure, because we are going to talk about how these cells stand forces. So these forces are thanks to this kind of things, and also they are responsible for movement, for contraction, for different ways that the cell behave. And finally is the outer membrane, which is also an amazing part of the cell, which is responsible for just the outer boundary of the cell, but it has also some very interesting properties. Is that the membrane of the cells have this what is called fluidity, that it's like a bidimensional fluid. So the movement is restricted upon the surface and it moves like a fluid. So it is a very interesting stuff. And the membrane has some gates that help to communicate. So in these four main parts, you can see where the genetic information is, that is going to determine how the cell behaves. You can have also the inner structure that it is mostly water. You can have this skeleton, which is responsible for stand forces, but also for movement or for contraction or this kind of behavior. And finally, the outer membrane, which is responsible for communication. So this is all the things that you need in order to create a biological system. Then these cells are organized in tissue. So this is histology. You have on this picture, you see these 4 different kind of tissue. So you have here connective, epithelial, muscle tissue, and nervous tissue. So you see these are kind of the same scale. So it is like, you can imagine like being here and you see, for instance, one of them is the wall, another one is glass, another one is people, another one is floor. So with this very different material, you can create a room for a course. So these are very, very different, and they are. What is interesting is that they are made with the same genetic information. So this is funny. So as you see, it's now think as a physicist for a while, even if you are not, and you have not this very interesting quality. Try to think as a physicist. So if you think as a physicist, you see that this is very heterogeneous. So if I have to model this, I start with the problem because it is very heterogeneous. It is very, very complex. What it is written in this Humphrey's paper, that it is very nice, is that as long as you make your computational model more complex, you will see that you get more homogeneity, even if it is that heterogeneous, because you see plenty of homogeneity in the way that tissue behaves. I can show you these kind of pictures about tissue, but if you kind of press your finger, you will not feel something puncturing. I mean, you are not going to feel this heterogeneity. So which means that inhomogeneous system is can produce very homogeneous response. It's from the computational point of view, it's its behavior is very highly nonlinear. You will see all this in these 3 days. You have these kind of things in tissue especially. It's inelastic, it's viscoelastic, it dissipates energy as it contracts and as it expands. It's very heterogeneous, it's anisotropic. It varies in time, and what is worse, it varies from individual to individual. So you have this very high variability, which makes very difficult in order to simulate. I mean, if you think about water, water is always water. Air is always air. But tissue is not always the same. It's very, very different. So again, it's multiphasics, it's multiscale, and strongly coupled. So the components of soft tissue are cells, which I've been talking before, but it is not just cells. You have this extracellular matrix. So cells, as I said before, well, this is more or less what I've been telling, but it is not just cells tissue. Then you have this extracellular material, which is it's responsible for the microstructure of tissue. It provides strength and resilience. So when you push, it's a combined action when you make some force against tissue, it's a combined action of cells and extracellular matrix. So if you think about from the engineering point of view, it looks like a composite. It's a composite. It's like fiber and a substrate. So it's a composite. So this makes that the behavior of this composite material is different than the individual parts. It works in a combined way. So it provides this strength and also the resilience to waste, for instance. Extracellular matrix is not just it is not inert. It is biologically active. So it is also provides a way of this environment for the cells. So it provides a way of that the cells can be alive and also can communicate. So one cell communicates with the other through crossing this extracellular matrix. And if you read a bit more, you'll see that it is the main components of this are collagen, elastin, and both of them are providing strength and structure. And proteoglycan, with this very strange name, is kind of the smart guy, because this is responsible for communication between the cells. Now let us go up and think about this continuum mechanics. I show you that it is very heterogeneous and anisotropy. But the way that we simulate things is, in our case, is continuum mechanics. We are not going to simulate cell by cell. We are going to simulate tissue or muscle. So how can we go to continuum mechanics if it is not continuum at all? Well, this depends, of course, in the scales. As I said before, you can simulate water as continuum mechanics, but water is made of molecules. So the fact is that if you go at a certain scale, then you can think about, it's like doing an average of the properties, and you can do it. With tissue happens the same. First of all, there is this constitutive relationship. Constitutive relationship of tissue is how these stresses are related to strain. I mean, this is like a spring. If you get some spring and you just pull this spring and you try to reach the spring, what you're going to see is that an opposing force. If I try to move the wall, you're going to see an opposing force. So this force is proportional to the strain. How it is proportional to the strain? Well, this is a very simple relationship. So this is force, this is the formation, and this is the proportionality constant. Well, it is not a constant, but it is the proportionality parameter, let's say. So you will see, just forget about well, if you're curious, do not forget, but forget about these indexes because they are related to, well, you're going to see this during the course, but this is, which means that this is a tensor, this is a tensor, this is a tensor. So it is the behavior, this proportionality between strain and force can be very, very complex. This is what I mean from that. And this relationship comes from the deep structure of tissue and its reaction to forces. So in order to guess This is a force, so this is something that you can measure. This is displacement, you can measure too. But how can we establish this S? So this is related to, in order to do this, you have to really study the deep structure of tissue in order to guess this S. Now, once you have done this, this relationship between the force and between the displacement, you can use this here, and you can just have a differential equation. So, well, this is at every point. This is for a full domain, for instance, for a bone, let's say, or for a body, or for a heart, or for a artery wall. So this is the differential equation that is going to model the behavior. So you model this behavior in time, you model this behavior in space. This is no more than a force balance. So this is the second law of Newton. This is force equal to mass times acceleration. It is no more than that. So you have this equation where you can relate. You have related forces and displacement. You have this equation in order to study the evolution of tissue. But then I said before that this is multi-scale and multi-physics coupling. So you are not going to have only one equation. You are going to have plenty of equations with plenty of unknowns. All of them are going to be coupled. And this is what it is at the system level. So we've been working at the lower scale with the constitutive relation. Then you are moving one scale up, which is for the behavior of each of the individual system, and then we go for the behavior of the full system. All these equations can be very tightly coupled. That is to say, imagine that we are studying how a heart pumps blood. Then with a pumping heart, you have electrophysiology, you have electrical activity that is propagating along the muscle. This electrical activity is making the muscle contract, and this contraction is making blood getting out of the heart. So you have at least, I count 3 different systems that are coupled. Each of the system with its own set of differential equations. But all of them are tightly coupled. You cannot solve one isolated from the other. So this is the multi-scale and multi-physics character. So it is like you have this local behavior with the constitutive model. You have this global behavior thanks to using these force balances equation for each of the problems individually, and then you have this system behavior. All along this course you are going to see same example. Not even if you are working at molecular dynamics, you will see the same thing. It's always the same thing. I mean, maybe the equations are not the same, but it is same idea. So this was kind of an introduction, and in this introduction you will, I hope that it was kind of a good panorama of the kind of things that you are going to see in the course. So I wanted just to finish, give you a few minutes if you want to make any question, but I wanted to finish with this, which is not science, but it is, well, it's funny. So in the first half of the talk, I was talking about our code, which is called Alia, and I said that Alia Red is the things that we do in biomechanics. We started doing this in 2004. I talk about Mare Nostrum, which is the big computer there in the chapel, and you are going to see, Jasmine is going to give you one of these courses, a crash course on cardiac modeling using our code. So this is a beating heart. And you see here a quotation where it is naming all these kind of things, Mare Nostrum and Alia Red and this virtual human heart. It's a bit exaggerated, this statement, but however, well, it is done. So you can see this quotation. So what is interesting is who is saying this. So this is, if you buy that book, you will see that one character, this guy Winston, is talking about us in the book. So if you buy, and this is a novel, it's more recent than what we are doing, but it is funny. And when we discovered that this guy was talking about us in in the book. Well, right now what I should do is I should give you the book and say, open page 154, and you see. And then I don't know who is going to play my part in the next movie, but well, I hope that Dan talks to me and asks me about the actor. But well, anyway, so well, this was kind of the introduction. So if you have any question about it, and if not, at 11 just come back to the room. Yes,
So
that's it.
Before you talked to us about the mechanical, the mechanics, multi-scale simulations, and you have three system of equations. The third one, I'm not sure, talking about the system, organically, the whole system, what was Q? What could be Q in such a system? For example, what could be?
Yes. The for instance, in the case of the heart, this is a nice example. So in the case of the heart, this, as I said before, you can have you have three systems. So point to point, at each point, what you're going to have is you have a small piece of, let's say this is tissue. So you have a small piece of tissue, and at this tissue you can have this first row, which was the constitutive law, the one that relates displacement with force. For the electrophysiology, you have at this level you have the cell model for electrophysiology, how this electricity is created from displacement, for instance, or from concentration of the different ions. And in this case, also you're going to have here. So this is tissue, or let's say this is muscle, and this is blood. So you can have here blood also. So blood, it's a fluid. So in this fluid, you have also this point relationship between displacement and forces. In the case of fluid, is a relationship between velocity and forces. So you have a differential equation for simulating how this electrical field is propagating. You have one differential equation. You have another one that relates contraction with the forces. And in fluid mechanics, you have another equation for modeling the forces also inside the fluid, which relates where you can get information on the pressure and velocity all along the fluid. Pressure is a force. So pressure and viscosity are the forces that are here at the surface, separating the solid and the fluid. So then you have three differential equations, one PDE for the electrophysiology, another one for solid mechanics, and another one for fluid mechanics. But all of them cannot be solved independently because all of them are related. So this last part of the system is that you have to do something in order to solve them coupled. And what is interesting is that, as I said before, you can use some numerical method for solving one, the other, or the other. When you and all these methods are working properly. Once you put them all together, then everything is screwed up. Because to solve a coupled system is not like solving the sum of the addition of the individual system, but it is much more complex. Any other question or comment? No? Okay, then if not, it's time for a break, and coffee break is coming here. So thank you.